also remember what we did now. It was the very last slide we saw. We talked about flooded graphs and flooded graphs. And I want to present one result by Postnikov that relates this back to the cells we see in the polytroid cells in the slide. So this is the result. If I have a reduced flooded graph, so called reduced, is this property that it's defined in a way that is not really intuitive and not easy to check by definition. That when we have a flooded graph and we start performing these moves 1 to 3 on the flooded graph, all the other flooded graphs we obtain will be called equivalent and move equivalent. And it's in that whole class of move equivalent graphs, we never encounter a single flooded graph to which we could apply this reduction procedure. Then the flooded graph is reduced, right? So we assume in this result that our flooded graph is reduced, that it is perfectly orientable, and so then it is perfectly orientable. I'm sorry, that's really the consequence. And the bound measurement map gives a subtraction-free rational parameterization of the corresponding non-negative corresponding set. So this cell, these cells were corresponding to matroids, and MG was the matroid we associate to a flooded graph via the source sets of its perfect orientation. And okay, so this says then, in this case, this is a subtraction-free rational parameterization. That's great for total positivity, because if we start with the flooded graph and all of these labels are positive rational numbers, hence the whole cell will be total. Right? So this is one way to verify that a matroid, if it corresponds to a reduced flooded graph, gives us a positive cell. And we have some more consequences here. So from the flooded graph, we can read off the dimension of the cell. It's going to be given by the number of the faces. Sorry, there's a cardinality missing here. The number of the faces of the graph minus 1. And moreover, if you have me another cell that is a positroid cell, then this result tells us that there exists a flooded graph so that the cell is obvious. So any positroid cell has associated with it a class of reduced move equivalent flooded graph. And the last point, if we have two different parameterizations of two different flooded graphs, G and G prime, of that parameterize the same cell, then they are related by. Okay, so this is like a complete answer of how to combinatorially characterize the positroid cells of the Grassmannian. Any questions on the result or comment?
If you replace the non-negative Grassmannian cell, you only go from positive real numbers?
Yes, but then we have to include a wider class of flooded graphs. So yeah, so the totally positive Grassmannian is one cell in the totally non-negative Grassmannian. And if you want to just know about the totally positive Grassmannian, you have to study just maximal flooded graphs, so the maximum number of faces, the boost, and so on. But this result includes all cells, all dimensions. Okay, so this is the result for it.
Yes, I'm asking if you can get the closure, or just the open part.
So I think about the totally non-negative Grassmannian as being the closure of the totally positive Grassmannian.
But let's say you have some positroid cell that's actually smaller, and then you get other positroid cells in its closure. So do you get them as well in this parameterization?
So you get every positroid cell. Every positroid.
No, for each positroid cell is open, so you just
Yeah.
get the open part with this fixed Levy graph.
Yeah.
If you want to go to the boundary, you have to erase some edges and stuff with Levy graph, and then Levy graph for the
Yeah.
positroid cell in the boundary.
So the Flavy graph will change because
Yes.
yes, but this result includes all. So even the boundary one, yes, and I'm not exactly sure how much is known on how what the operations are on the Flavy graph to get to the boundary.
Yeah, I mean, yeah, there's some combinatorial rules to understand what is the dimension of the resulting Levy graph if you arrange some edges. So if you raise an edge and Levy graph is reduced, then it goes in the boundary.
If you allow weights to be 0, then you get these things in the boundaries as well.
Yeah, but it's a bit tricky because sometimes you have to go to infinity with a certain ratio, so going to 0 to a certain ratio to hit a certain boundary. So it's a bit tricky. It depends on parameterization, but combinatorially it's straightforward. There is a rule to understand if there is an edge, what happens. If the dimension drops by 1, you go to the boundary. It can drop also by 2, so you go to the boundary of the dimension 2. So there are some combinatorial rules for that. But from the parameterization, it's not straightforward to understand how to go to the boundary. Sorry for
No, that's great. Any more questions? Okay, so then let's move on to the, okay, this was the list of references. We mostly saw, yeah, a mix of Postikow's paper and Lawrence paper, which I was recommend a lot, lecture notes on positive Grassmannian stuff. Okay, so today we're gonna pass through, we're gonna pass the second topic in the title, to cluster algebras. And there's a little summary of what we're gonna see today. I'm gonna relate it back to positivity and positivity tests for the Grassmannian 2n, which is just the combinatorially nicest, easiest example, and helps me to motivate cluster algebras, although maybe in the audience will not be that necessary to you're all here. And yeah, then we're gonna go through the buildup of cluster algebras, some fundamental structural theorems, and get back to the Grassmannian and see what's the cluster algebra associated this case. So I took this from my standard colloquium talk on cluster algebras, where I usually spend some more time on motivating cluster algebras, because depending on the audience, they might think I'm very eccentric in my math. So here's a bit of a not complete picture of where we can find cluster algebras in mathematics and beyond. So if you have a favorite topic like algebra, combinatorics, ontology, geometry, topology, or more in the physics direction, theoretical physics analysis, just choose your bubble and see if one of the topics mentioned interests you. I've marked the ones that are coming up more. So here is getting amplitudes, you have total positivity, and Flavy graphs. So this is the topics that we're touching on in these sections. And yeah, if you have more bubbles to add, also I'd be happy to hear, because the area is really growing fast, and it's hard to keep track of all the applications that are coming up. And then here's a bit of the history. So Fomin and Zalevinsky introduced cluster algebras in 2001. They're about 24 years old. And they came out of exactly the study of totally positive matrices that we've been looking at in the last lecture. So we'll be kind of starting historically in the right order in these lectures. And so given like totally positive matrices, also quantum groups and canonical bases with canonical bases, especially the second two topics led to first a lot of movement in representation theory, a lot of interest in the subject from representation theorists, lead theorists. But then we already saw, and you know by now, that it's grown fast around its origins. And yeah, people of the area are very proud that we have our own classifier in the math and in the MCS classification. Okay, good. So let's get to the math. This was just to get everyone's attention back in case it was a bit too technical on the slide before. And we're just going to go through the example that we've seen already last time, a little reminder. So we saw the total positivity. So in the case of the Grassmannian 2-4, it translates to checking that if I have an element of the Grassmannian 2x4 matrix of full rank, real entries, that all its political coordinates, all the maximum minors, are positive numbers. So this was the example we've seen, except now this was a 5, there was a 6 on the other example, which was the letter type of my slides. But yeah, so this is an example of a totally positive matrix, or totally a point, a matrix representing a totally positive point in the Grassmannian. The reason I give it is that this example serves to observe that in contrast to the case of totally positive square matrices, we don't care about the entries, like the signs of the entries. We can have negative entries in the matrix and it can still be representing a point in the totally positive Grassmannian. And another thing to mention here, I mean, the points in the Grassmannian are the vector spaces. The Grassmannian is inside the projective space. So if I have a matrix representing a point in the Grassmannian whose Fluker coordinates are all negative, then that also serves me as a point in the totally positive Grassmannian, just because they can be scaled and then still ends. Okay, so there's a few signs that can appear, and still we're in the totally positive. Great. Okay. So if we go a bit deeper, this was the exercise from yesterday, right? Checking that Fluker relations for the case d equals 2 are of this form. We have 3-term Fluker relations, and one of the terms has a sign different from the others. Great. So these relations help us when we care about positivity, because we can express one of the Fluker coordinates in each such relation as a sign-free or like a positive rational expression of the others. Like, in fact, Laurent in this case. So in particular, in the case of Grassmannian 2-4, to check if a point is in the positive Grassmannian, we just need to evaluate 5 out of 6 coordinates. And of course, if the dimension grows, if n goes larger, then there's a greater significance. Like, we're not saving a lot of time here by not computing one either. But yeah, with growing n, this becomes significant. And here's a nice way to visualize positivity tests and the relation of the two positivity tests we can observe here. And that is by associating them to the edges of a triangulation of a foregon. So yeah, and there's really not much to say. If I draw a foregon, or a quadrilateral, there's 2 ways to triangulate it. And depending on the choice of diagonal, I can associate a collection of Fluker coordinates, choosing their indices at the edges that appear. And then the 2 positivity tests correspond to the 2 triangulations, and they're related by this. So, yes, this example directly generalizes to the Grassmannian 2, and so we have a few bijections. The first one here is the efficient totally positive test for the Grassmannian 2n. So a collection of Fluker coordinates that when all of those evaluate positively, then all Fluker coordinates evaluate positively on a given point. The second is triangulations of the n-gon. And the last one that I've added in here, we're going to see how this last bijection goes later, is reduced Levi graphs of tent of maximal dimension. Okay, there's a few words missing here, but we're going to get into that. So if we want to verify that a given point in the Grassmannian 2n lies in a totally positive part, then it's enough to check dimension of the Grassmannian +1 many Fluker coordinates to see if this is the case. And what kind of Fluker coordinates we need to check? Well, we need to check Fluker coordinates that correspond to a triangulation. Okay. Any questions? So this is the motivating example and the motivating dynamics to pass to the coordinates, to cluster algebras, I'm sorry. And in particular, I'm gonna generalize this idea, the structure that we observe in two ways. First, I'm gonna generalize the combinatorics. And if we always keep playing with triangulations of an n-gon, we will always just see the totally positive TP test for the Grassmannian plane. So we're going to generalize that. And we're also going to generalize the algebraic component that we associate, right? So we have two components. One is the combinatorial object, and the other is the algebra that we associate and the relations we get. Okay. So from triangulations, we're going to pass to quivers. A quiver is a directed graph. In representation theory, people prefer to call them quivers and not digraphs. So when someone talks about a quiver, most likely there's an algebraic component that they have in the back of their mind.
It's a question on Zoom. They raised their hand. So I actually don't have panelist access right now.
And there's a hand.
There you go.
Okay. A link to the presentation. Yes, there will be one on the website after these potential typos on this.
Actually, it's just.
That was it.
Sorry, Antoine, I saw your hand was up, so if you put a question in the Q&A, we'll see it typed out.
Or also unmute yourself.
They can't unmute themselves.
Oh, they cannot. I'm sorry. Okay. Type it in the chat. Yes.
Sorry.
Great. We're good. No, yeah, it's good to remember that there are people on. Okay. So right. So let's go through the combinatorics, the combinatorial layer that we need to define cluster algebras, and that's quiver. We have this technical assumption on our quivers that they don't have any loops or loop cycles. And we're going to decide, so we have a given quiver, we're going to decide to split the vertex sets into parts. Some of them are going to be called mutable vertices, and some of them are frozen. The frozen vertices in my talk will always be marked in blue, just to remember that they're frozen. And this is a choice I can make from the start. I can also have all frozen or all mutable vertices, but the outcome or what I'm going to construct from a given quiver will change and depend on this choice. And given a quiver, we're going to now, so the quiver is going to substitute our triangulation. The quiver mutation is what's going to substitute the flip operation that we have on a triangulation. And the mutation is a three-step process that's defined as follows. So for the mutation in our quiver, we choose one mutable vertex. And we're going to perform a local operation that only involves this mutable vertex and its neighbors. The first step is considering all the paths of length 2 oriented that pass through my mutable vertex. So for any such path, if k is my mutable vertex, any path I, k, j, I add a direct arrow omitting the mutable vertex in the middle. In the second step, I invert all the arrows that are incident to my mutable vertex k. And in the third step, as step 1 and 2 might result in creating oriented 2 cycles, I remove a maximum collection of 2 cycles from my. Okay, so my arrows are not labeled, so it doesn't matter which arrows move in this last step. It's just important that after doing it, you don't have any 2 cycles left. Okay. So there is an exercise on the sheet where you can check that this is an involution. So if you fix your mutable vertex k, you perform the mutation at the vertex k, and then after that, in the new quiver, the new mutated quiver, you again decide to perform the mutation at k, you should get back the same quiver. If you didn't, check again.
And we assume no 2 cycles, and then remove a maximal set of 2 cycles.
Right. So in my original quiver Q, I start with a quiver that does not have any 2 cycles. but steps 1 and 2 might create them two-sided.
Gotcha.
And why? I mean, if you imagine this one would be an oriented triangle, so I've got another arrow from J to I in my quiver, then adding this arrow in creates a two-cycle, and I want to get rid of that out. Okay, so I think I'm good on time. So if you want, we can take a quick break, and if you have a phone, you can scan the QR code. If you have a laptop, you can type the link, old school, and go to this very nice Bernard Keller's website. And he designed like a Java program where you can perform quiver mutation in like that. So if you do, you can. I would recommend to all of you, if you want to learn about cluster algebras, you should do the mutation, quiver mutation, a few times by hand, just to kind of understand the process. But for solving the exercises, I think especially there's one exercise on the sheet where I would very much recommend using this app. So for the people in Zoom, if you didn't take the So in case you were in Zoom, people see this now, right? Yeah.
You need
Share. Okay, so here's the website. And if you scroll down a bit, you're gonna see this little window where you can design your own quiver. This is always the starting one, but you can also get a new quiver, and then just by dragging and dropping, adding arrows, adding nodes first, and then add some arrows. Okay, great. And then there's a nice, well, now you can start mutating by just clicking on the nodes, and you will see how the quiver changes. And there's also one very nice function that I like to repeat just in talks, just to show that this is actually quite a complex combinatorial procedure that explodes. You can do random mutations. I'm going to do 30. And see what happens to the graph. So the program does not draw multiple edges. Instead, it puts these numbers on the edges. And well, I started with a quiver to go back that had a few double arrows, but really not much more. This is the one I started with. It looks a bit innocent. But if I go to this random repetition, 10 section, no, you can see how the number of, oh, no, it's not. Wow, that's interesting. You can see how the number of arrows pretty quickly explodes. So, yeah. That's all. If you want to play more, there's this program. If you actually want to get into it, I would recommend to download it, because it also has all the algebraic functions that we'll see in a second, and the algebraic definitions. But for the exercises, the quiver exercises, this is good, a good tool. Any questions?
So in the last step, when you said that you remove two cycle, you remove both edges.
Yeah, the complete cycle. The complete cycle. And if you have multiple cycles, or you can form multiple cycles, get rid of all. You do this until there's no more oriented cycle. Okay. Let me switch back to the slide. Great. So this is for you to play with. And yeah, just see what you get. So it's useful to think of this mutation process as some kind of discrete dynamical system, where we start with our quiver Q, the one I gave you in the start, And from that quiver, depending on the number of mutable vertices, we can walk in several directions. Every vertex in this infinite and regular tree corresponds to a quiver I can get from mine by doing a sequence of mutations. After checking that the mutation is an involution, I will know that this tree is in fact n regular. So if I mutate again on the same direction, I'll just walk back to where I came. And this is kind of the evolution of what quiver mutation, what kind of quivers I can get from a given one through this mutation. Okay, so then let's get to the algebraic layer. It's what would replace the Plucker coordinates and Plucker relations that we saw in the case of the Grassmannian 2n. So as this whole the combination of a quiver with this algebraic datum is called a seed. I think probably they chose the name because kind of a cluster algebra grows out of it, at least that's how I imagine. So to our quiver, we will associate a tuple of variables that are called cluster variables. And also here I'm going to have this distinction of having some associated with mutable vertices and some associated with frozen vertices. And when I perform a mutation in the quiver, I will also simultaneously perform a mutation to this collection of variables. And how that looks is the following. So if I fix my k mutable vertex of Q, then the pair after mutation, I get a pair again of tuple of variables and mutated quiver. The mutated quiver, we already saw what it is. The tuple of variables will change in just one slot. I will replace only the variable in the k entry of my tuple. And this is the mutation formula or the exchange relation that will tell me what to replace it with. It depends on the quiver and the arrows incident to my vertex k. So for every arrow that goes into k, I will add the corresponding, and it starts at a vertex I will add the variable xi. So here, careful, this is really the product taken over arrows. If I have two arrows from I to k, then I will have xi squared appearing. And then the second term similarly considers all the arrows going out of k. So for every vertex j, for every arrow k to j, I add the variable xj. And I divide by the variable xk, and that's what I put in place of the k variable in the. Okay. And another exercise on the sheet is checking that also this operation is an. Okay.
This is kind of a cruel question. Do you know how to complete the following sentence? That is the unique formula that satisfies.
That's the unique formula that satisfies.
How would you finish that sentence? That formula is the unique formula that satisfies. Like why? Why? Yeah. I mean, I know that it works, but okay. I said it was a cruel question. We can discuss it like that.
Okay, yes, I would love to discuss it. In this case, so for me, starting with Plucker relations and so on, I would get back to the case of the triangulation in a second, and we see that this is exactly what I need to do to generalize the feature Plucker relation. But I easily believe that there's much more to this formula than that.
Are you asking the combinatorial level or the fact that there are monomials and not other things? Because there are generalized cluster algebras involve polynomials that are, I mean, they're not just the sum of two monomials, but a higher degree.
Of course.
That also satisfies the positive Laurent phenomena.
Yeah.
But I don't know if you're asking why in terms of like combinatorics of arrows or in terms of degree of what happened, what appears. I guess both.
It was really more to stimulate conversation than
Okay.
a serious question.
Yeah, there are generalizations, so
Yeah.
there's several around positivity.
Okay, there's several ways to generalize this. One, we don't even have to generalize this formula to more terms, but we can get rid of the quiver and consider more just matrices. That could be incidence matrices of the quiver, but also generalize those. There is many approaches, and we're going to get to positivity and Laurent phenomenon in a second. Yeah, now I'm intrigued by this one. I know it's just because I didn't answer yet. over that. Okay, what's the next slide? I forgot. Great. Okay, yeah, we're gonna do an example. And this is like the first non-trivial example that everyone does. When you work with cluster algebras and you think like something should be true, this is the example you turn to. If it doesn't work here, then yeah, you can give up. Like this is the best example we have. So we're going to perform the whole mutation circle. I left the formula up here. This is a very convenient notation where instead of placing the numbers at vertices, I immediately place the variable. So if I'm performing a mutation in direction 1, what do I do? What happens to the quiver? We can do this quick. I don't expect you to actually think long about this. I think this is rather easy example. So please also answer in case you're bored. Just get through this fast. What happens to the quiver? Or maybe I should put it on the slide. Right, there was 3 steps in the quiver. First step, adding directed for every path with 2 arrows, we add an arrow. When we just have 1 arrow in the quiver, we can forget about that part. Second one was turning the orientation around, flipping the orientation of all arrows incident to my vertex where I will mutate. Okay, that one becomes relevant. And then the last one was deleting the 2 cycles, which again will not be common. Okay, so mutation in this quiver is only always flipping the orientation to 1 arrow. Okay, so what happens to the variables? If I do mutation in direction 1, okay, second variable stays. I said I'm just going to change the one associated with my first vertex. And here's the formula of what I do to the first variable. Right, so I'm going to compute these 2 monomials depending on arrows in my quiver. Let's start with the first one. All the arrows going into 1. How many do I have? 0. So what's like the monomial? Yeah, it's just 1. This is a convention. If there's no arrows, the monomial is 1. And the second one, what do I put there?
X2.
X2, exactly. And then I divide by x1, right? So this is the monomial I get. So the new variable I get. And yeah, I flip it. Okay. Next step. Gets a bit more interesting. Oops. Oh no, I clicked already. Okay, let's just do it. So next step, I repeat the same procedure, right? I get 1 for the empty monomial, there's no arrows going in. And this term for the second monomial, there are arrows going out, and I divide by x2. So this is the expression. And then the next step becomes even a bit more interesting. Right, again, arrow turns, we keep the variable in the first spot, in the second spot, we change this variable. And we replace it by, well, an expression that already gets a bit nasty, right? Because we said this variable is one of the monomials, 1 is the other one, but we have to divide by this Laurent polynomial. And so this is the calculation we should be doing. And well, it turns out simplifies, and we can factorize, and we get back an expression that is and in this case, this is we've already kind of freed ourselves, and we made it to the other side. Because if we continue in the calculations, we'll be seeing more and more simplifications until we in fact come back to a seed where the set of cluster variables coincides with the set of cluster variables we had. The quiver coincides up to labeling with the quiver that we had. So in this case, we're going to identify these 2 because we have a quiver isomorphism that is just an element of the symmetric group moving around the labels of the quiver. So that after performing that operation, the quiver looks the same as what I started with, and the set of cluster variables also looks the same. Okay, these 2 conditions is what I need to identify quivers in a sensible way, identifying seeds and seeds. Questions or comments?
There a reason why you went 1, 2, 1, 2, or could you have done like, could you keep mutating at 1?
Yes, no, I mean, yes, I could.
But then you
there's
undo the previous
exercise.
step,
Yeah,
right.
exactly. So it's an involution, so I could do 1, 1, but I would always come back. I could have started with 2. That's sure, like that was a choice. I could start with 2, then 2, 1, 2, etc.
Did you say in the case of triangulations, what are the frozen variables?
Yes, the frozen variables, and we're gonna see this in a second, are corresponding to the boundary.
I see.
So the boundary in the triangulation is what we don't change when we flip. The internal arcs is what we change, so they would correspond to neutral vertices. The boundary is found. I didn't put any frozen variables. Okay, so then we're done. We're done. We're ready to define the cluster algebra, and put the whole thing up at once. So for the cluster algebra, I would focus on all these cluster variables that I collect when I do my mutation procedure, and I'm going to define it inside an ambient field. That for me, and it's going to be a certain subalgebra generated by all these variables that I found along the way inside my ambient field. My ambient field is a field of rational functions that has as generators any set of cluster variables. So I start with a field of rational functions in n plus m variables. N plus m was the number of frozen plus mutable vertices. If I have a seed, and I mutate this seed, I get another seed as prime, then this new seed as, so I start here with the seed whose cluster variables are the generators of my ambient field. And if I obtain my another seed as prime, then that will satisfy that my ambient field is also generated by this. Okay, so this goes into the definition of a seed. Great, so this is my ambient field. Any seed that I get generates this ambient field, and then the cluster algebra is the subalgebra generated by all these cluster variables that I found along my mutation. Okay. And there's a result, one of the first results in the first paper by Fomin and Zerwinski, telling me that the cluster algebra does not depend on the quiver I start with, but rather its mutation class. Okay, so if I have the whole pattern of seeds with quivers and cluster variables, it doesn't matter which one I choose to actually generate this, I will always get this. Okay, so
Is there some, I guess, is there something deeper to that theorem? Like, that feels obvious to me that if you, like, if they're mutation equivalent to things generated by all these variables that you mutate to.
I mean, a bit, right? Because if I start with my seed, you choose a quiver, you associate this first collection of cluster of variables to it, and those will always be the generators, right? So if you give me a quiver, then I would already automatically assume that those are the clusters are the generators of my ambient field. And that will change, right? If you start with another quiver, then the expressions that you get for cluster variables here in the original ones will be quite different, right? So it's not obvious, because the combinatorics of the quiver very much determine what kind of expressions you will find along the way.
Apologies if you're kind of just answering this, but when you do these mutations, you don't change the field, right? It stays the same. Is that surprising? My algebra is not that great. If you were to randomly make rational functions of your variables, you would get different fields in general. Right?
That's in particular that whatever seed I have, the collection of cluster variables are algebraically independent in that field, which is not clear from the mutation process. If you do it once, yes, okay, we can check it by hand. But if we keep repeating the mutation procedure, we get more and more complicated rational expressions. And so this result, or this says that it doesn't matter how many mutations you do, if you take this collection of elements in your field, they will be algebraically.
Thank you.
Just one question off Zoom. Antoine is asking, is it sometimes true that the cluster algebra is isomorphic to the quotient of the ring of polynomials in the cluster variables modulo the ideal generated by the exchange relations?
Yes, this is the case in type A or the Grassmannian 2n. But I think this might be the only case where that's true.
Could you repeat the question? Sorry.
Is it sometimes true that the cluster algebra is isomorphic to the quotient of the ring of polynomials and the cluster variables modulo the ideal generated by the exchange relations?
So what is true in general is that you have to so if your cluster algebra is of finite types, you have a finite collection of cluster variables. That's the first thing maybe to add to this question so that we're not working in infinite polynomials. And then we have to saturate the ideal of exchange relations to actually get the presentation. Any more questions? Okay, so getting back to the example that we did, along the way here, we collected, besides our first two generators, 3 more cluster variables. So our cluster algebra is the Z algebra generated by these 5 elements in my ambient field of rational functions in 2. Okay. So in general, cluster algebras are defined over Z. We don't need any other field. But when we start identifying them, there's always like this question of extending the coefficients and working on complex numbers. But to define them, we just need to work on them. Okay, so a few more things we can observe in this example. First, very nice thing. I mean, I told you, okay, you should think of quiver mutation as a discrete dynamical system that, quivers labeled as infinite and regular tree. In this example, we didn't really need that infinite tree, right? We just have 5 different seeds and then we return to what we started. So there's periodicity in this example. And the other thing is that, in fact, although we said, okay, cluster variables, they always live, they're rational expressions in the starting variables. Here, in fact, we only encountered Laurent polynomials and they only had positive coefficients. There are plus and minus 1 here, which is misleading because the example is small, but in general, that they only have positive coefficients is true. So the first result that Fomin and Zelebinsky proved is called the Laurent phenomenon. And it tells me that in my mutation procedure, whatever cluster variable I encounter, it would always be a Laurent polynomial in the variables of my original. So in fact, combining with the other result that the cluster algebra does not depend on the quiver but just its mutation class. So any cluster variable is a Laurent polynomial in the cluster variables of any other seeds. Okay. I don't know if that came out like grammar-wise understandable, but yeah. Okay, so cluster variables are always Laurent polynomials and they have integer coefficients. But Fomin and Zelebinsky also in this first paper observed that in whatever example they compute, the coefficients are all non-negative. Or not true. And this conjecture was very popular in the area, and it stood for quite long until 2014. I think it's the archive. The date Grassmannian and Kontsevich posted a paper on the archive that actually proves that this conjecture is true. And it's a bit of and I should add way more references because this is the most general result, more general than what we need here. And there's been a sequence of papers before where people were able to prove this conjecture in less generality or for certain quivers or for certain matrices. And this work has mostly been done in representation theory using tools like categorification. And it was not possible to solve this conjecture with these tools. And Grassmannian and Kontsevich completely changed the point of view on cluster algebras and considered them as certain rings or certain functions on certain log-Flavial varieties that are called cluster varieties, and used tools from birational geometry and inspiration from mirror symmetry to, in fact, turn the coefficients into a counting point. So we now know, more importantly, that the positivity conjecture is also true. And then here is the second important result that Fomin and Zelebinsky proved in their second paper, and that's the finite type classification. So the question here is, if you give me a cluster algebra and a quiver, when do I know that the set of cluster variables is finite? And here's the condition. So the cluster algebra associated to a quiver is of finite type if and only if the mutable part of the quiver is mutation equivalent to an orientation of a Dinkin diagram. So here are the Dinkin diagrams of type ABE. If your quiver after some number of mutations looks like an arbitrary orientation of one of these, your cluster algebra will have a finite collection of clusters. Okay, so the example we did was the one of type A2. Okay, great. Okay, so then we can connect this back. Or should I wait a second? Any questions? Okay, so then in my last 10 or so minutes, let's relate this back to the Grassmannians. First to the Grassmannian 2n. So we already convinced ourselves that the efficient total positivity tests for the Grassmannian 2n, okay, this should definitely be real numbers here, sorry about that, are in bijection one-to-one corresponding to triangulations and one. And I already mentioned or alluded to that we can pass from triangulation to quivers. So you can think of quivers as generalizing this picture that we saw for triangulation. And the way to do it is the following. The mutable vertices of my quiver will correspond to the diagonals or internal arcs or chords in my triangulation. Frozen vertices will correspond to boundary edges. And then inside of every triangle of my triangulation, I add an orientation. You can choose the orientation of this triangle. It's just it's a convention, just be convention. And then the last point after doing all that, we can forget about arrows between frozen variables. You can keep them if you like, but they will not affect the outcome or the cluster algebra. So just like a general convention of deleting these arrows, just to simplify. Okay. And then, oops, great. So if we do this with the example of the Grassmannian 2-5, the quiver we would associate here looks like this. So I've chosen the arcs 1, 1, 4, and 1, 3 to triangulate. These will become my mutable vertices of the quiver. Then I have the blue vertices corresponding to the boundary or the frozen vertices. And if I perform a flip on this diagonal 1, 3 on the left side, changing it to the diagonal 2, 4, the resulting quiver looks like this, and then it's an exercise, and the exercise to check that this gives me a commutative diagram if I perform the corresponding mutation. Okay, so the observation here is if I start with the triangulation, that the quiver associated with the flip triangulation is the mutation of the quiver associated to the
Can you say again what's the orientation of the arrows?
Yes, so I chose clockwise orientation for arrows in each triangle. So in each triangle of my triangulation, I will draw this picture. But you might as well change and have all the commands. So yes, so okay, so this small example hopefully convinces you that the following statement is true. We have a bijection between the set of all triangulations of an n-gon with the operation being the flip of the diagonals and the set of seeds. Okay, maybe I should say quivers associated with the triangulations with the mutation process. Passing to the algebraic level, we have this bijection extends. So if we associate flipper coordinates to the triangulation, and we perform the Plucker exchange the Plucker relation corresponding to a quadrilateral as we change, that this also corresponds to the seed mutation or the mutation of the cluster variables on the other sides. So I would try to reformulate the slide a bit. Yeah, so the point is to say that the seed mutation formula generalizes the three-term correlation that we see, or that corresponds to the split. And in this way, then we obtain a bijection between the seeds of this cluster algebra and the efficient total positivity. And the cluster algebra in this case then corresponds to the polynomial ring generated by Plucker coordinates, the modulo Pluckerization. So this is the example where the answer to a question is positive. Great. And then we have similar results regarding the homogeneous coordinate ring of the Grassmannian Kn, which we'll check now, and then also for GLN and SLN and partial flag varieties, Schubert variety, and the list of varieties that I put here keeps growing every year. Okay, so then the last thing for today, let's see how we can generalize from the Grassmannian 2n to the Grassmannian Kn. And we're going to do that using Flavic graphs. So if we have a Flavic graph, we're only going to be working with reduced Flavic graphs from now on. We can assume, as you checked in the exercise, that it is bipartite, that all edges connect black and white vertices. And then we can associate quiver to the Flavic graph using the following steps. The mutable vertices of my quiver will correspond to internal faces, faces that don't touch the boundary of the disk. The frozen vertices will correspond to those faces that lie along the boundary. And then arrows will be perpendicular to edges in the Flavic graph and oriented so that the white vertex is on the left. So here's an example that I copied from the paper of Laura, screenshot it. So you could ignore the face labeling for now, but this is my Flavic graph, then this is the outcome. So for example, if we check the arrow connecting the face here labeled by empty set and by one box, then the white vertex lies. So to every Flavic graph, in this way, we can associate a quiver. And then another ingredient that I tell you how to get seed is what's the algebraic data, what are the cluster variables I associate. For the triangulation, I always just associated the Plucker coordinate with the labels corresponding to the endpoints of my edge. So what am I going to do here for the faces of the Flavic graph? I'm going to use certain combinatorics of paths passing through my Flavic graph that are called trips. So trips are paths that for Flavic graphs of type Dn start in a boundary vertex and end in another boundary vertex. And they go through the Flavic graph following what's called the rules of the road, meaning that when I start walking from my vertex, I hit an internal vertex of my Flavic graph. It's going to be black or white, and depending on its color, I choose where to go next. If I hit a black vertex, I turn maximally right. So if my black vertex, I come into my black vertex, I have several edges connected to it. I go out of the most right one. And if I go into a white vertex, I do the opposite, I go out of the most left. And so trips then start in the boundary vertex, end in the boundary vertex, and they divide this into paths. And they also come oriented because the trip I started at the vertex I. So in particular, I can talk about the right and the left side in the Flavic graph, where faces that lie to the right, faces that lie to the left of my trip. And I will start labeling faces with the indices I, depending on which side of my trip they are. So in particular, what I choose as my labeling here is placing the index I to every face to the left of my trip Ti. And the lemma here says that, and check that as an exercise, I can give you a reference, that doing this for every I, walking through all the trips, this will result in a face labeling where every face has exactly d many indices. So I associate this way d element subsets of 1 to n to every face in my Flavic graph that was of type Dn. So the seed I will associate will pick up these labels and take them as labels from the components, just in the way it's. One more data point that I can associate with my Plavix graph here is the triple permutation. So defining a permutation sigma g associated to g by checking for the trip ti what is its end vertex will give me a permutation. Yeah, where I define sigma g of I. Okay. No, I don't have an example. I'm sorry. And then questions about this. Okay, at this point, I would definitely recommend to take the small example before that we had on the exercise sheets and do this trip permutation for at least one, and then see what are the labels you get. I think, oh, actually, I think this is an exercise. I don't know. I didn't put it. Okay, maybe it's on the sheets, it's not on the slides. Yeah, so one exercise is taking this quiver that the Plavix graph we saw, as a running example, computing the permutation and computing the seed that I. Okay, so then let me end with this result by it's a combination of results, a mashup of results of Scott and Postnikov. So Scott has a paper called Grassmannian cluster algebras, where they proved that the homogeneous coordinate ring of the Grassmannian Kn in general is a cluster algebra, and the cluster algebra structure for it you can obtain it this way from Plavix graphs. It's not the combinatorics Scott used, but there's an equivalent combinatorics called Postnikov diagrams, alternating strand diagrams, where there's another translation of combinatoric bijection between those and Plavix graphs. So to get to this cluster algebra, we're going to need to focus on a special class of Plavix graphs. And we're going to determine them by their permutation. So the sigma k, let that be the permutation that deranges moves the first let it be this permutation. Sorry, the words don't come up. So 1 goes to k plus 1, 2 to k plus 2, etc., all the way up to the end, and then I go from 1 to k. So if I choose a reduced Plavix graph that has this triple permutation and associate the quiver to it in this procedure that I explained, and then I associate a set of cluster variables to it, or variables, according to the phase labels I got from my trips, then this is a seed in the cluster algebra AKN, which is isomorphic to the homogeneous coordinate ring of the Grassmannian in its Flickr heading. So up to the detail that here I change my field to complex. So in particular, or as it's not a direct consequence, but one can verify that this way we obtain a bijection between reduced Plavix graphs with this given trip permutation, and then as an operation on this set of Plavix graphs, I will allow square moves. And on the other side, I obtain, so let's consider the Plavix graph modulo the moves 1, 2, and 3, which were the merging of vertices and the ignoring or exerting vertices of degree 2. And on the other side, I can consider seeds in this cluster algebra where the tuple of cluster variables consists of only Flickr coordinates. So this is a finite set, both are finite sets, and the right set here, the right-hand side, is contained in the set of all seeds of this cluster algebra. But if I go beyond the Grassmannian, I think starting at 4, 8, the set of all seeds in this cluster algebra is infinite. Well, this is always a finite collection of particularly nice seeds in this cluster. Okay, so there's like a finite list of Grassmannians that are, well, besides Grassmannian 2, and that are 3, 6, and 3, 7, 3, 8, that are a finite type, and beyond that, the Grassmannian cluster algebra has infinitely many seeds that cluster. Okay. I think I would stop. Yes.
Are there any other questions for Lara?
Just to check if I understood, so X, the length of X here is the dimension of the Grassmannian.
Plus one.
Plus one, right,
Yes.
because you need the F like for.
Yeah.
Okay. I see, so and then mutating means you want to parameterize it differently.
Yeah, exactly, I'll change parameterization. We always stay, so in getting back to maybe the cells, the positroid cells, we always stay in the same maximal positroid cell. Don't change the cell, but we do change the parameterization.
All right, let's thank Lara again.